What's up, everybody? This is Wallace from A3Academy, and today we're going to be talking about work and energy. So basically, let's get started right quick. So first of all, we need to define what work is. And the best way I think we can define work is using an example. So let's get started. So suppose I had an object here and I exerted a force called, say, F, and that force pushed the box a certain distance, and we'll call that distance D. And so we can define the work as the magnitude of the force times the distance. So work equals Fd. Even better, if we knew that the force was operating at an angle, say, and that angle was called theta, then we know that the work exerted on the object is going to be force times distance times the cosine of the angle theta. So here's an example of how we calculate work. So suppose we had an object here that's being pulled by this white string, and this white string is being pulled with a force of 80 newtons, and it's being pulled at an angle of 30 degrees. And when I say that the angle is 30 degrees, I mean that the force is operating in this direction and the box is being dragged in this direction, which means that the angle between these two directions is 30 degrees. Anyway, suppose that I drag this box across the floor, and I drag the box a distance of 1 meter. Well, we can calculate the work that we have performed on the box just by applying the work formula. And simply that is work equals force times distance times the cosine of the angle. 80 times 1 times cosine 30 degrees, which should give us 69 joules. Now just keep in mind, joules is the unit that we will use for work and for energy. Now for another example of work, suppose that we applied 10 million newtons of force to a brick wall, but the brick wall remains stationary. How much work have we performed on the wall? Well, again, we know that the work is equal to the force times the distance times the cosine of the angle. But we also know that the distance that the brick wall travels is 0 because it's stationary, which means that the total amount of work that we've exerted on the wall is 0. That illustrates an important point. No matter how hard you push on an object, if that object doesn't move, you're still doing 0 work. Now, a concept that's very closely related to work is energy. Energy is considered to be the ability to do work. So there are two important types of energy that we're going to be covering in this podcast. So here's the first one. Suppose we had an object, 5 kilograms, that's held at a distance of 3 meters above the ground. This object, since we're holding it above the ground, has something that we call gravitational potential energy. And gravitational potential energy, also known as G.P.E, can be calculated with this simple formula. It's just the mass of the object, m, times the acceleration due to gravity, g, times y, which is the distance at which it is held above the ground. In the case of this object, the gravitational potential energy is going to be m, which is 5, times g, which is 9.8 meters per second on Earth, times 3, which is the amount of meters at which it is held above the ground. We can calculate this and we will get 147 joules. We can still calculate the gravitational potential energy of the ball now that it's on the ground. Using the same formula, we'll get 5 times 9.8 times 0 since the ball is 0 meters above the ground. Using this formula, we get that the gravitational potential energy is 0 joules. Now, let's take a look at what we had to start with. We started with 147 joules of gravitational potential energy. After we dropped the ball, we ended up with 0 joules. The change in gravitational potential energy was 147 joules. Now, why do we care about the change in gravitational potential energy? Well, because it's closely related to work. In fact, the general principle is that work is equal to the change in gravitational potential energy. What does that mean? That means that if we want to change the gravitational potential energy of an object, we need to do work. So, since the change in gravitational potential energy, as we said before, was 147 joules, the work that gravity has exerted on the object to make it fall to the ground is also going to be 147 joules. Now, there's a different type of energy, not just gravitational potential energy. Suppose we had an object that is in motion, say a 5 kilogram object that's moving at 10 meters per second. We can say that an object in motion has a property known as kinetic energy, or Ke, and we can calculate the kinetic energy of an object using this simple formula, 1/2 times mv squared, where m is the mass of the object and v is the velocity of the object. Now in this example, the kinetic energy of this ball traveling at 10 meters per second is equal to 1/2 times 5 kilograms times 10 squared, which is 250 joules. Now suppose we wanted to exert a force to increase the speed of this object from 10 meters per second to 20 meters per second. Since we're exerting a force over a distance, we are technically performing work on the object. How much work? Well, we know that the initial velocity of the object was 10 meters per second, and the initial kinetic energy of the object was 250 joules. Now, the velocity of the object is 20 meters per second. Once again, using the formula Ke equals 1/2 mv squared, we can calculate the new kinetic energy of the object, which is 1,000 joules. Now remember we said earlier that work is equal to the change in gravitational potential energy. Well, that's also true for kinetic energy. Work is the change in kinetic energy. So we can find the difference between our final kinetic energy, which we calculated to be 1,000 joules, and subtract the initial kinetic energy that we calculated to be 250 joules. And this gives us 750 joules, which means that in order to accelerate a 5 kilogram object from 10 meters per second to 20 meters per second, we will have to exert 750 joules of work. So there you have it. Work is equal to the change in gravitational potential energy. Work is also the change in kinetic energy. But how are gravitational potential energy and kinetic energy related? Well, we know that by the law of conservation of energy, the total amount of energy has to stay the same from beginning to end. In other words, the gravitational potential energy plus the kinetic energy has to be equal to the gravitational potential energy plus the kinetic energy at the end. Here's an example. Suppose we had a ball at the top of a hill, and this ball is rolling at a speed of 5 meters per second. We also know that the height of the hill from top to bottom is 10 meters. Now, if we let the ball roll all the way to the bottom of the hill, it'll be moving at a certain speed. What is that speed, given that the height of the hill is 10 meters and its initial speed is 5 meters per second? Well, we can easily calculate the speed of the ball when it's rolling at the bottom of the hill using the law of conservation of energy and the formulas that we previously discussed for finding gravitational potential energy and kinetic energy. So let's start. Well, first things first, we know that the gravitational potential energy of an object is equal to mass times the acceleration due to gravity times the height at which the object is positioned, mgy. We don't really know the mass of the object since it wasn't given to us in the problem, so we have to treat it as an unknown variable and leave it as it is. But we do know the acceleration due to gravity is 9.8 meters per second squared, and we know that y, the height of the object, is 10 meters because the height of the hill is 10 meters. So the gravitational potential energy is equal to 98, which is 9.8 times 10, times whatever the mass of the object is. We'll call that m. So the gravitational potential energy is 98 m. Now, we can find the kinetic energy in the same way. We know the formula for finding the kinetic energy of an object is 1/2 mv squared. 1/2 times the mass of the object times the square of the velocity. Once again, we don't know the real value of m, so we're going to have to treat it as an unknown variable. But we do know the velocity of this object in this case is 5 meters per second. So we can calculate the kinetic energy in terms of m is going to be 12.5, which is just 1/2 times 5 times 5, times whatever the mass of the object is. We'll call that m. So the total of the gravitational potential energy and the kinetic energy before the ball rolls down the hill is going to be 110.5 m, meaning 110.5 times whatever the mass of the object is. Now that we found the total energy of the object before it rolls down the hill, now we need to figure out what the total energy of the object after it rolls down the hill is equal to. Once again, we use the same strategy. We know that the gravitational potential energy of the object is 0. Since it's at the bottom of the hill, it is 0 meters above what we call ground level, which means that the gravitational potential energy is going to be just equal to 0. We know the kinetic energy is equal to 1/2 times mv squared. We don't know the mass of the object because it wasn't given to us in the problem, and we don't know the velocity of the object since it's what we're trying to find out. So we're going to have to just leave kinetic energy as it is with both of these unknown variables. Now the total of gravitational potential energy and kinetic energy of the object after it rolled down the hill is going to be equal to 1/2 mv squared. Now you might be thinking, well, how are we going to solve for two variables? we don't know the mass, how are we supposed to find the velocity? Well, first of all, let's take a look at our law of conservation of energy. Our total before has to be equal to our total afterward. So let's put these two values together in an equation. 110.5 m is equal to 1/2 mv squared. Now at first glance, this equation seems ambiguous. But we know automatically that, since m is on both sides of the equation, we can cancel out m, giving us the equation 110.5 equals 1/2 v squared. Then it's really easy to just solve for v, which is 14.9 meters per second, which means that after the ball has rolled down the hill, it is moving at 14.9 meters per second. That is the basics of work and energy, especially gravitational potential energy and kinetic energy. We went through a couple problems and examples, and I hope you've learned something from this podcast. So I'm Wallace signing out from A3 Academy, and as always, the more you know, the better you are.